Greetings and welcome to my talk. My name is Rachel Bosch. I'm a lecturer at Northern Kentucky University. Today I'm going to be describing to you an example that points out the vulnerability of carbonate critical zones to extreme geomorphic events. I'd like to start out by thanking John Martin and the steering committee for the Carbonate Critical Zone Research Coordination Network for making this session possible. So what do we mean by extreme geomorphic events? These are catastrophic events which result in extreme land surface change, such as floods, tsunamis, landslides, lake outbursts, and debris flows. And then for the carbonate critical zone, you've probably already seen this slide today, but our carbonate critical zone is on the right, and contrasting that with the end member of a silicate critical zone, which has porous media groundwater storage and is on an order of magnitude thinner than the carbonate critical zone. The area that we're looking at today is the central Kentucky karst. So if we look at this portion of the world karst aquifer map on the western hemisphere, we're zooming in on the eastern United States and looking at Kentucky in that green starred area. And we zoom in a little bit further so we can look at this digital elevation model of the central Kentucky karst, where you can see the Green River, which is the base level, flowing across the top left of this figure. Just to the south of that is the Chester Cuesta or upland. Below the caprock of that Chester upland is where we find Mammoth Cave, Fisher Ridge Cave, Vinegar Ridge Cave, and the other large caves of the central Kentucky karst. The edge of those cave networks is delineated by the Chester Escarpment, which runs kind of across almost east to west on this figure, and to the south and southeast of there you see the Sinkhole Plain, which is the recharge area for this aquifer. Today, we're going to be focusing on a debris flow event that occurred in Mammoth Cave a little more than 1 million years ago. This paper is in press for the Journal of Cave and Karst Studies with co-authors Dylan Ward, Aaron Bird, Dan Sturmer, and Rick Olson. Before we proceed, I would like to take a moment to thank all of the people who have explored and made possible the work that happens today in Mammoth Cave, beginning with the late Archaic and early woodland people about 5,000 to 4,000 years ago. Then in the 19th century, the slaves who were cave guides and tremendous explorers of Mammoth Cave, including Stephen Bishop and pictured in the upper right of this slide, Matt Bransford and Nick Bransford. Then the first explorations into the area of Mammoth Cave where this project took place include Pete Hansen, Carl Hansen, Claude Hunt, and Leo Hunt. Pete Hansen and Leo Hunt are pictured in the lower left. Then in the lower center is a group of folks in this iconic photo from 1972. If you look at the tall person in the white helmet, that is John Wilcox, and he drew a map that was essential to this project. And then this project would not have been possible without the support and guidance and the first geological interpretations done of this area by Art and Peggy Palmer, who are pictured on the lower right. And I would like to acknowledge that all of the field work done in Mammoth Cave National Park is done on the traditional lands of the Eastern Band of Cherokee Indians, the Cherokee Nation, the United Kiowa Band of Cherokee Indians, the Shawnee Tribe, the Eastern Shawnee Tribe of Oklahoma, the Absentee Shawnee Tribe, and the Chickasaw Nation, all of whom the Park Administration continues to be in contact with about land management. Our hypothesis for this project is that this large pile of rocks that was found inside of Mammoth Cave was the result of deposition by a debris flow that entered into Noah's Way through a now obscured entrance. So this person is standing in Big Avenue. They're pointing at Mount Ararat. You can see the large rocks that are in there. These are sandstone blocks, and the ceiling is this smooth limestone ceiling. You can see that there hasn't been much breakdown that's happened in this passage. The passageway up to the right where she is pointing is Noah's Way, and it was most likely completely full with this deposit of Mount Ararat at some point over 1 million years in the past. This deposit consists of Big Clifty sandstone ranging from clays and silts up through boulders on the order of 1 meter in diameter. It's chaotic and unsorted, often it's roughly inversely stratified. So these larger boulders are up at the top of the deposit, and it takes a mile of travel in the cave in modern day to get to this deposit. So the methods we used to test our hypothesis about this resulting from a debris flow included map analysis, including surface maps and cave maps, sedimentology, 3D imaging of the pile, and then some near-surface geophysics to characterize the subsurface. The maps that we used included this map by John Wilcox, which is on the left, which you can see has an area of some large boulders pointed out. This is Big Avenue that comes along here. This is Noah's Way. So at the junction, you have this large pile of rocks. There's a slope along here. There's this passage that drops off sharply off to the east, which is quite significant. We'll come back to that. He noted sandstone breakdown, so that's remarkable. And then he noted this borehole, which is this pipe that was in the ceiling that was used in the early 20th century to provide food and other supplies to explorers in that part of the cave. Also, there are surface topography contours on this map. So we were able to easily correlate this map with the topographic map and the geologic map, and then use GPS to go out into the field and find the surface expression of that borehole that was used to send supplies to the early explorers. And so we were able to stand there and see what the surface is like above Noah's Way and imagine where there may have been an entrance at some point in the past that allowed this material to get into the cave. Looking at what's inside of the pile, we did some grain size analysis. We used a combination of sieving of the matrix material along with a grid analysis looking at the largest or dominant grain size diameter inside of each box, and then treating it like a two-dimensional grain size analysis like you might do with microscopy. We combined these two approaches to make a full grain size distribution, which is consistent with the interpretation of a debris flow deposit. To characterize the surface of this, we had this serendipitous encounter with this person in the blue helmet, Tate Jones, who expressed his interest in doing some terrestrial LiDAR inside of a cave. So we connected him with our project. He and his coworkers from KCI Technologies volunteered and brought their supplies up to Mammoth Cave to scan the surface of Mount Ararat and the surrounding passages in Noah's Way and Big Avenue, which resulted in this point cloud on the upper left and the resulting 3D model that you can see here on the center left, which looks remarkably like this wonderful photograph taken by Art Palmer on the lower left. So to add to our characterization of this pile, we wanted to find out where the base of the pile was, so we used electrical resistivity. Due to the sensitive nature of this resource, we were able to run only one array for electrical resistivity survey down the established passage in Big Avenue. Our raw data and our inverted data in modeling the layers below Big Avenue is in the center. And then on the right is our interpretation of this stratigraphy. So from 0 to 0.25 meters below the trail is trail material. From 0.25 meters to 0.75 meters below the trail is the chaotic debris flow material. And then beginning at 0.75 meters below the trail is vuggy limestone bedrock. So putting this all together, we were able to isolate this 3D model of the pile of Mount Ararat. So we have the LiDAR surface and then the inferred base from the electrical resistivity survey, which allowed us to estimate the total modern day volume of this deposit at 3,400 cubic meters. The length of the deposit from its tail all the way along its spine to the head is 75 meters, and then the maximum relief from the tip of the pile vertically down to the inferred base is about 7.5 meters. Trying to reconstruct the picture of what things were like when this was deposited, we wanted to look at the paleoflow possibilities in Noah's Way and Big Avenue. So we used two different approaches here. We used a shear stress calculation to predict what kind of flow velocities would be needed if the larger grain sizes in this pile, so these are grains going from 0.2 to 1 meters, if they were entrained in a bed load flow, what would be the velocity needed for that incipient motion? And that comes out to be about 5 to 12 meters per second. Then we looked at the scallops on the bedrock walls surrounding Mount Ararat. These range from about 1 centimeter to 2 centimeters in length, which according to Bloomberg and Curl's equations gives us an estimated paleoflow velocity of about 1 to 3 meters per second. This range of paleoflow estimates correlates well with Jim Van Gundy and Will White's estimates for flow velocities associated with a major flooding event in Mystic Cave in West Virginia, which they had at 5 to 9 meters per second. So another way we were able to look at the LiDAR results to interpret the topography of this pile was to import that LiDAR surface as a digital elevation model into QGIS. And so then we were able to extract a series of topographic profiles along the deposit, and when we do so, we compare this with our profile of a typical debris flow deposit, and we see that Mount Ararat was most likely deposited from two different debris flow surges. So we have our tail back here, and we come along, and then we have the primary head of Mount Ararat here, and then our secondary deposit, starting at about the same tail, would come here, and then there's another head here. And we also see these accumulations of larger grain sizes, both at the head of the primary initial deposit, and there's an accumulation of larger grain sizes right here at this secondary head, and then a fining here, and then they coarsen again as you come along the deposit. So looking at some of these cross sections, if you look at cross section A, you can see this drop off, and this is where that natural face was exposed, where we did the grain size analysis. And then B is the cross section taken at the secondary head. C, you can see this, that there's kind of a flat area that shows this local minimum between the head of the secondary deposit and the continuation of the tail from the first deposit. And then the next one that I want to point out is D, where it looks a little bit flat, but if you see this little divot on the right, it is really quite significant. There is a small channel that runs along the eastern side of Mount Ararat, right along here that you can see in the DEM, which turns out to point to a significant part of the evolution of this pile as we see it today. And so the story we can tell from these analyses is all put together in this geomorphic map that we created of Mount Ararat. And so what we think is that there was an event on the surface, a flood or a landslide or some kind of a natural lake burst event that caused all of this mass of material to move into a now obscure entrance, which would be on the modern day valley wall near where we were standing near that pipe out in Doyle Valley. And so that material moved in, and in the first surge, it created the this large debris flow pile that's outlined with these thick dashes. There was then an erosion event along the side where we see that stream, and either at the same time or following, there was this second debris flow deposit that's outlined by these dashes. And then the final event that we noted was the erosion down this eastern side passage, and that's what cut through both of these debris flow deposits and allowed us to analyze the entire cross-section of the debris flow. So, in conclusion, the results of this field work supported our interpretation of Mount Ararat as having resulted from a debris flow event or events. It would have been a minimum of 2 surges creating this pile. We calculated the modern day volume of this deposit at 3,400 cubic meters and calculated paleovelocities in this passage of happening in the range of 1 to 12 meters per second. Our initial hypothesis was supported. There was sandstone that originated out in the surface in Doyle Valley with 2 debris flow surges into a now obscured entrance in Paleo Doyle Valley. So here you see the reconstructed paleo surface and our approximate location of where there may have been an entrance over 1 million years ago. This would have washed more than 3,800 cubic meters of material into the cave, some of which was subsequently eroded by that side channel and down the side passage. All of these events point to the significance of extreme geomorphic events in caves and in carbonate critical zones in general, and it just emphasizes the vulnerability of these systems to influence from many, many different factors. In addition to the landscapes themselves being vulnerable, humans who live on karst are vulnerable, particularly to water scarcity and water quality issues. The Carbonate Critical Zone and Society Working Group of the Carbonate Critical Zone Research Coordination Network is working to address these issues. We have identified 2 questions to investigate. One focused on stakeholder engagement in research. That is, how can we advance our science and its communication by engaging local stakeholders? And the other addressing environmental justice. Do differences in critical zone characteristics contribute to inequitable provisions of environmental goods? We are continuing to welcome new voices to this working group. If you are interested in this research, please talk to one of the steering committee members for the RCN or contact me at boschr1@nku.edu. Thank you for watching my talk.